Hello? Hello? Hi, how are you? Good? Okay. Today, we want to discuss the biomechanics of musculoskeletal tissue. We discussed the structure. Now, let's see the biomechanical features of the musculoskeletal tissue. Because we need to know their biomechanics when we want to design something to replace them or to augment them or to uh, help them. There are some basic concepts in biomechanics. I am sure you are familiar with them. The first one is stress. Stress is the amount of force that is applied to one point of an object and it is usually, uh, not usually, always expressed in force per area or pressure or stress. It is not pure force, it is force per area. That is why the unit for stress is not Newton, it is Pascal, the unit of pressure. And when this stress is applied to an object, the object changes. And the amount of change or deformation created by this stress at any point is referred to as a strain. The accurate definition of a strain is the amount of deformation divided by the original length before deformation. So you have a dimension like L, you apply an stress, this dimension changes. How much this dimension changes? The change is expressed by delta L. So the amount of change is delta L, and we divide delta L by L, and the result will be the strain. Since the units of L and delta L are both the unit of length, so a strain is dimensionless. It doesn't have any unit. You are familiar with this graph. This is the stress, a strain on the horizontal bar, a stress on the vertical bar, a stress, a strain graph. And it shows when you increase the stress, how the strain changes. The behavior of materials on this curve shows how elastic, how plastic, how brittle, how tough, how strong they are. In the first part of this curve, we have the elastic part. And in the second part, it is the plastic region. The elastic region means if you remove the stress, the material or the object will return to its original length or shape or whatever it was. In the plastic region, when you remove the stress, some of the deformation remains. So we call it plasticity, but in the first region, we call it elasticity. We said this curve shows the amount of change in strain with respect to stress, based on the stress. So the slope of this curve in the elastic region, which you can calculate this slope by dividing the stress by a strain at any single point, is called modulus or modulus of elasticity or Young modulus, and it shows the elasticity of the material, how the material reacts under stress, how elastic the material is. If the slope is too high, it is vertical, it means you need a large stress to make a small change in the strain. So this is not an elastic material. But if the slope is too low, it means with a small stress, you will have a large strain. So the material is highly elastic. So the larger the modulus of elasticity means the material is less elastic. This slope in the elastic region is usually linear, but in some materials, when it come close to the plastic region, gradually it loses its linearity and have some curves here. When the material starts to deform as a plastic material, this point is called yield strength, and this property is called yielding. So when the material loses its elasticity and starts to behave like a plastic material, this behavior is called yielding. In plastic region, the material continues to deform without breaking. And at the end, at a point, the material starts to fail. This point is called ultimate tensile strength or ultimate strength. And this failing continues until it reaches to full failure or fracture. We call it ultimate tensile strength because we usually calculate this uh, curve under tension, but we can calculate it until shear, under compression, but generally it is calculated under tension. When a material enters the plastic region after the yield point, it gradually becomes harder and harder. It means with the increase in stress, you have increase in strain, but the material, although it is under plastic deformation, but you need more stress to have more strain. This region is called a strain hardening. A strain hardening. After the ultimate strength point, the material starts to fail and gradually fails until the fracture point. This area is called necking. By necking, we mean the material starts to become thinner and thinner, like a neck, until it fails. So necking starts in the ultimate strength point. We have ductile materials and brittle materials. We have tough and soft material. Let's see what's the difference. First, if we calculate the area under this curve until the material fails completely, until the fracture points, the area under this curve is equal to the energy expended to fail the material. And it is equal, based on definition, equal to toughness. So if we have a larger area under the curve, the material is tougher. If we compare these two materials, one with blue curve, the other with green curve, the area under green curve is larger than the area under the blue curve, the surface area. So the green material is tougher, but a material that has a short plastic range, it has an elastic range and suddenly enters the plastic range and then breaking point. And usually in these materials, the modulus of elasticity, or a slope of this curve, is too high. This material is called brittle. They do not undergo plastic deformation before failure, or at least a very small plastic deformation. They have a small elastic change, and then suddenly they enter the plastic, and then they fail. But ductile material has a large plastic region. It undergoes a lot of plastic deformities and necking, and then fails. The failure is not sudden. So this is the difference between brittle and ductile material. And you see here again, the area under this curve is much smaller than this curve. So it is a tougher material than the blue is tougher than the red here. And also the brittle one, the blue one is brittle and it breaks suddenly, but sorry, I said blue. The red one is brittle and it breaks suddenly, but the blue one is ductile. It undergoes plastic deformation and necking and then fails. Stress strain curve that you usually see is like the red one here. Actually, this is engineering a stress strain curve. The calculation of a stress a strain is different. In engineering, we have another one that is called true stress strain. And the difference is in calculating the strain. In engineering one, which you are familiar with that, we have an L, the original length, and several delta L's. And we divide each delta L to the original length. So the length is always L, the original length is always L. And we divide these different delta L's, delta L1, delta L2, delta L3 to L. It becomes the engineering curve, which is the red one. But if we use instantaneous L, for example, we apply the stress here, we have a strain, so L was without a stress, we have a delta L divided by L become the strain here. When we apply another stress, we have another delta L2. We divide this delta L to the L2 here, not the original L. So if we have any change, we divide it to the L in the previous step of the exam, of the test. That is why the result will be almost a linear curve. And if we want to compare accurately the properties of two materials, we need the true stress strain curve. Engineering stress strain curve shows you a general concept about the material, but if you want to compare them for their properties and provide, for example, a material that is closer to bone, you need the true stress strain curve. So let's see the biomechanical behaviors of different tissues. This is a general presentation of a stress strain curve for a healthy bone and an osteoporotic bone. This is the elastic region, and then yield point, plastic region, ultimate strength, and then fracture. At the beginning, we have a low slope, and then it increases rapidly. This is due to viscoelastic behavior of the bone. This is another one comparing. These are for your record to have them comparison between ceramic, stainless steel, and bone and different tissues. The biomechanical behavior of bone depends on the structure we discussed, the gross structure, the shape of the bone, the microstructure, the orientation of the osteons we discussed, and the orientation of the microstructure of collagen fibers. These three determine the biomechanical behavior of the bone. But it is not the only thing that defines the behavior. The rate at which the load is applied to the bone, orientation of the load with respect to the microstructure of the bone, and the type of the load that is applied is very important. Before continuing, let's discuss the concept of viscoelasticity, because tendon, cartilage, and bone are viscoelastic material. They are not pure elastic, they are not pure plastic, they are not pure viscous. They are viscoelastic material. Viscoelastic materials are materials that exhibit both viscous and elastic behaviors at the same together, not at the same time, together. And they provide when they are under a stress, they provide a time-dependent and rate-dependent strain. It means based on the rate that the load is applied. And more importantly, based on the time that the load is applied, they have different behaviors. Let's see this video. Here the load is applied very fast. slide very slow. So you saw the difference. This is a classic example of viscoelastic material. The behavior when the load is applied very fast is different when the load is applied slowly. First, the elastic behavior of this material is like any other elastic behavior. They can return to their original shape after the force is removed. And you are familiar with elastic material like springs. They are called Hookean solids. Robert Hooke defined the behavior of a spring, so that is why they are called like with this name. But viscous behavior is the behavior that the material shows under constant stress. As long as the force is applied, the strain and deformation continues. And this is the behavior of Newtonian fluids. But when you combine these two, you have a non-Newtonian material that is called viscoelastic. Viscoelastic material is between these two. It is not purely elastic. When you apply the stress, it cannot undergo full elastic deformation because the viscous part does not allow rapid changes. And when it is under constant stress, it is not like viscous material, pure viscous material that undergo constant deformation. They exhibit, because the elastic part prevents this constant deformation in the viscous phase. So you have something between full elastic and full viscous behavior. The most important thing about these materials is they are time dependent. If you apply the stress faster in a shorter time, they behave like a rigid material. If they apply the load slowly, they have time to behave like a viscous material plus an elastic material, and they gradually change in shape. Beside that, they have creep. Creep is a behavior and a characteristic of viscoelastic materials. When you have a constant load on viscoelastic material, the load doesn't change, but the material gradually changes. And this change is called creep or creeping. So at first, there is no change, but gradually the material under the constant load gradually undergoes change in the form. It is called creeping, and it continues. Sorry, I don't know what did he do. Come here. It was him. Sorry. And at the end, the creep leads to failure and rupture. Another, so creep is a form of deformation. We will see it in our biomaterials when we use them in joint replacement because they are under constant load, and this constant load gradually over several years, they change their shape. Another property of viscoelastic materials is stress relaxation. When you apply the stress to viscoelastic material, at first, the stress increases and strain increases. But gradually, based on based on the material, this time that strain increases depends on the material. But at a point, stress relaxation appear and gradually the stress decreases. You are applying the load and load is constant. At first, the stress increases in the material, but gradually starts to decrease due to viscosity of the material, due to fluidity of the material. And another important property is hysteresis. Hysteresis, when you apply the load to viscoelastic material and you release the load, if the material has not ruptured completely, it returns to the original shape. Actually, in viscoelastic materials, they want to return to the original shape, but due to the interaction between viscous and elastic parts, some part of this load dissipates as heat due to friction and the need to changes in the material. This load, some part of this load will turn into heat and it will be lost. So the material cannot return to its original shape. This is another property of viscoelastic materials. When you apply the load and release the load, it doesn't return to its original shape. Based on the structure of the material, these hysteresis can be very small or it can be large. The importance of these hysteresis is for one single cycle, it is not important. But if it continues and the cycles are repeated, the next cycle will be here, the next one, as you see, the next one, and gradually it leads to the failure of the material. So it is important to consider during the repetitive loading. The viscoelastic materials are frequency-dependent materials, the frequency of the application of the load. So viscoelastic material under frequent load application or dynamic loading show two different moduli, a storage modulus and loss modulus. A storage modulus is the elastic portion of the material, the response of the elastic portion of the material. And loss modulus is the elastic motion of the response of viscous portion of the material. The elastic portion is recoverable part. Viscous is not recoverable part. That is why it is called loss modulus. This is loss modulus, the lower one. The upper one is storage modulus. If we divide loss modulus to storage modulus, we calculate the ratio between these two, loss modulus to storage modulus. It shows the behavior of the uh, of the viscoelastic material. It gives you the tangent of an angle that shows how viscous or how uh, elastic the material is. In other words, it shows how much damping it will give you. It means how much it can damp the load before failure, before having any change in the behavior. If this slope is high, it means you have high damping. If it is low, it means you have low damping. And in this way, you can see how your viscoelastic material behaves. Now let's return to bone. Bone is a viscoelastic tissue, but it is, although it is viscoelastic, but it is a hard tissue. Like any viscoelastic, any other viscoelastic tissue, bone behaves like one of them. First, the rate at which the bone is loaded is a very important factor to determine how the bone behaves. If the bone is loaded very fast, it behaves like a brittle material. If the load is applied slowly, it behaves like a viscous material and gradually changes its shape. So we can apply a large load to bone in a long time and nothing can happen, but we can apply a smaller load, but in a short time, and the bone will break. Some sports, you apply high load to lower limb bones during the exercise, but the bone doesn't break. But in a car accident, because the load is applied in a fraction of a second, even the load is smaller, but the bone breaks because the time that the load is applied is very short and the bone behaves like a brittle material. You remember the orientation of osteon or Haversian system in the bone, and we said they are aligned along the bone, along the length of the bone. The length of the bone is the dimension of the bone that the compression and tension loads are applied along it. So if the load is applied along these osteons, the bone is most resistant or is the strongest. But if the load is applied perpendicular to these osteons in transverse direction, the load is weakest. You are familiar with the concept of anisotropic material. These materials are materials that have different properties in different directions, like bone. The property of the bone, the strength of the bone is different along the length compared to the strength along the width. Here is a comparison between uh, ultimate strength in transverse and longitudinal directions along bone. you see the compression strength in longitudinal direction is much larger than the compression strength in transverse direction. And the same for tension. So the bones fail easily when the load is applied in transverse direction, but it can resist larger loads when it is applied in longitudinal direction. And here it is a comparison between the modulus of elasticity of femoral cortical bone. Uh, you see in longitudinal direction, it is 17, but in transverse, it is 11, and in shear, it is 3.3, only 3.3. So it means cortical bone is weakest in shear. Our bones are strongest in compression because the major load that is applied to our bone is compression. But while we are applying physiological load to our bones, they, they are not under pure compression. One side is under compression, the other side is under tension, but the tension side is usually small, but it is there. So the bone must resist compression and tension at the same time. The resistance against compression, because most of the load is compression, is much higher than tension, but still it is a strong in tension. What we discussed was about the lamellar or cortical bone with the dense structure. But you remember, in the middle part, the cortical bone forms the periphery of the bone. But in the middle, we have a large cavity filled with trabecular bone like this. It is not compact, it is not lamellar, it is trabecular, and it has lots of pores between the trabecula. So how it behaves? The behavior in this bone is different, completely different from cortical bone. First of all, we need to know the porosity and the apparent density of these trabecular bone or cancellous bone. When you have a solid object, the density, the bulk density is 100%. All parts of the solid object is filled with the particles, with the material. But when you have a porous material, some parts are occupied by something other than the bulk. For example, air or anything other than the bulk original material. So if you separate the bulk and the bulk of the material from the pores, there is a percentage of material filled with the bulk and a percentage filled with pores. If we divide the percentage of the solid material or the bulk to the whole volume of this block, it becomes the apparent or bulk density. The apparent density of cortical bone is 1.8 gram per cubic centimeter. You remember the cortical bone it has some pore inside it, but those pores are very small. But they are still there, and they are microscopic. But in trabecular bone, these are not microscopic. These are macroscopic. In trabecular bone, the apparent density is between 0.1 to 1 gram per centimeter, cubic centimeter. When you have an apparent density of 0.2 gram per cubic centimeter, it means the porosity of your trabecular specimen is about 90%. 90% of trabecular bone is filled with pores, not bone. When we apply the load on trabecular bone, first it behaves like an elastic material until it reaches the point of failure. The point of failure here is the failure for first trabecula. In this area, all the trabecula are intact. No fractures has happened, none of this. But at yield point, the yield point in other materials was for change from elastic to plastic. Here, the yield point is the beginning of fracture of the first trabecula. And this with one fracture, the slope decreases. With the second one, slope decreases more. And it continues until all the trabecula are fractured and the pores are compressed. With each fracture, one pore is a little bit compressed. And it continues until all the trabecula are fractured and all the pores are compressed and there is no more pore inside the bone, at least visible pore. And from now on, it becomes a solid material and it behaves like a solid bone or cortical bone, and it continues until it completely fades. So if we check the cortical bone curve and compare it to cancellous bone or trabecular bone, you see the trabecular bone or a trabecular bone with high porosity, you see it is almost a flat one until all the trabeculae are fractured, and then it behaves like a classic material. Uh, the amount of different mechanical properties, the amount of tensile strength or different properties, modulus of elasticity and comparison between them are easily available in the internet. So you don't need to memorize them. Just remember the when they compare them, remember which one is higher than the other one. For example, the cancellous bone is lower than the cortical bone is lower than all the metals, the polyethylene is lower than cortical bone. You can, if you remember like this, it's easier for you to remember to memorize them as figures. The cartilage we are going to discuss is hyaline cartilage. We said we have three types of cartilage: fibrocartilage, elastic cartilage, which are not inside the joints, and hyaline cartilage. Hyaline cartilage is the cartilage that covers the surface of the joints, and whatever we um, discuss is about the hyaline cartilage. Hyaline cartilage has several layers, And these layers from the joint surface to the bone surface, it has several layers with the different orientation of the fibers and the cells. The hyaline cartilage in the joints must resist compression, tension, and shear. The most important force is compression because of weight bearing and joint motion, but this motion sometimes create shear and sometimes create tension. This inside the joints is filled with a very small amount of a film or a fluid called synovial fluid, and it acts as a lubricant for the surface of the joint. If the surface of the cartilage is dry, it still has a low friction coefficient, but uh, when it is wet, the friction coefficient is about 0.001, and it's very low. And if it is lubricated with the synovial fluid, which contains hyaluronic acid, which increases the uh, lubrication there, the coefficient of friction of the articular cartilage will be 3 times lower than the friction of ice on ice. And you know, ice on ice has almost no friction, but still our articular cartilage has less friction than ice on ice. The surface of the articular cartilage is not totally smooth. It has some irregularities. When these irregularities come to contact from the other side of the joint, they may cause some frictions. But the fluid, including the large molecules of hyaluronic acid, comes in between and prevent these friction. This is called boundary lubrication. This is how the synovial fluid works. It is very thin and it causes these tiny interference between two surfaces to be eliminated. So one important behavior of articular cartilage is its low friction coefficient. So if we are going to reproduce anything to replace the articular cartilage, it must have low coefficient of friction. Otherwise, it is not working. When we discussed the structure of articular cartilage, I said it doesn't have a vessel and nerves. So the articular cartilage is depending on the synovial fluid for its nutrition. And we discussed how it works. When it is under compression, the fluid squeezes out of the cartilage into the surrounding tissue and the synovial fluid. And when the load is removed, the fluid returns back inside the cartilage and gradually brings the nutrition and oxygen with it for the cartilage cells. So this is how the cartilage uh, needs the loading, but this is not the only reason. Like any other musculoskeletal tissue, when you apply load on cartilage, the cartilage cells inside the cartilage sense this load and change their behavior to create a thicker and more resistant cartilage. So For example, I am a person that have a sedentary life. My cartilage will be thinner than a person who is a professional athlete, because the cartilage in the body of a professional athlete is under constant loading, and the cartilage cells, the chondrocytes, react to this constant loading and produce a thicker, more resilient, and stronger cartilage. But my cartilage will be thinner. So this is the second mechanism that load affects the cartilage. First, for nutrition and oxygenation. Second, for reacting to the load by creating a stronger and thicker cartilage. When we apply the load on cartilage, based on the magnitude and frequency of the load, the behavior of the cartilage will be different. If the load is frequent, or in other words, in better word, it has a frequency, it is not static, it allows the cartilage to resorb water between the loads and continue to live. But if the load is static, although we are applying load on the cartilage, but we do not give any chance to the cartilage to resorb any water from the surrounding tissues. So the cartilage will lack nutrition and oxygen and gradually starts to degenerate and break down. So for cartilage, static loading is detrimental, but frequent loading is useful. On the other side, the magnitude of loading, if cartilage is under excessive load, it gradually degenerates. But if it is under moderate load, it regenerates. So you have seen many professional athletes in heavy lifting that they have problem with their knee, hip, and spine in early 30s. But a person who is a professional runner has no problem with with the joints, because a professional runner is applying moderate loads to the cartilage, so he or she is protecting and regenerating the cartilages. But a professional weightlifter is applying excessive load to the cartilage, and the cartilage gradually degenerates and breaks down in these professional athletes. So be careful if you are going to be professional, keep in mind. This picture shows you how the different types of loading can affect the cartilage. And you see, if you apply the load and hold it, it hinder transport, so the cartilage will degenerate. But if you have dynamic compression or even dynamic shear, shear is detrimental to cartilage. We prefer not to have shear force in cartilage, but even dynamic shear is better than a static compression. A static compression is worse than anything. And all this is because of these structures that we discussed before in cartilage matrix, protoglycans, and how they behave in cartilage matrix to prevent compression and provide the damping effect. They are arranged like this, and they have they hold the water between their large molecules. So if we compress the cartilage, the water must be squeezed out of the space between these large molecules. So when the load is removed, they return, the water return and gradually occupies the previous space. And another mechanism was the negative charges. The negative charges here on the surface of these large molecules prevents them from coming closer to each other. So this is the second mechanism to provide the cushioning effect for cartilage. I said cartilage is viscoelastic tissue. And like viscoelastic tissue, it has gradual deformation. When you apply the load, it gradually changes. And when you release the load, sorry. And when you release the load, it gradually returns to its original shape. So this gradual change is important for us, and it prevents sudden changes in the shape of the cartilage in our joints. How this happens? In the first slide, I said cartilage has several layers. When we apply the load, the superficial layers toward the joint cavity first lose the water and they are compressed. And the deeper layers try to distribute their water between the other layers. And this gradually continues until all the layers have equal distribution of water loss. And when we remove the load, it happens in reverse. First, the superficial layers lose the water, and then again, the deeper layer and deeper layer until all the layers return to normal. So this is why we have this behavior. When we apply the load, first there is a sudden decrease in thickness, and then it gradually decreases. And when we remove the load, there is sudden increase in thickness and gradually it decreases. Again, this is for comparison between different tissues. You don't need to memorize them, but you need to remember that the cartilage, the strain care for the cartilage, if represented grossly, you see the between bone, tendon, and cartilage, you see the difference of shape of these curves and the distribution of them and the area under the curve. So you see for cartilage and tendon, it is large, so cartilage and tendons are tougher than bone. Any question up to now? No? The next structure is tendon and ligaments. Tendons and ligaments are structurally the same, but they are different structures in the body. Tendon connects muscles to bone. Ligament connects one bone to the other, but structurally they are almost the same. And these two structures, tendon and ligament, are designed to resist tension. They have no function in compression. You cannot force a tendon in compression to do something. They only work in tension. You remember when we discussed the hysteresis, we said part of the energy upon release turns into heat. In tendons and ligaments, this amount is 7%. So if they are under cyclic loading, in each load, they lose 7% of their uh, energy. And in other words, they have 7% hysteresis. Keep it in mind because later we use it. Tendons and ligaments are formed by dense, regular connective tissue, are the classic examples of dense, regular connective tissues in our body. The collagen fibers in these two organs are arranged parallel and they are in a parallel fashion. But here you see they are almost straight, but this is not true. They are a little bit wavy, but generally parallel. This wavy pattern gives them a stretching capacity for the first uh, maybe millimeter of a stretching or less than a millimeter of a stretching. The only difference between collagen in a structure, between tendon and ligament structure, is the ligament, the collagen fibers in ligaments is a little bit more wavy. So ligaments are able to be stretched a little more than the tendon because we need it. They connect the bones around the joints. We need a little bit motion in joints, so they have to be able to stretch. But for tendons, since they carry the force of muscle to the bone, even the slightest stretching is with slightest stretching in tendon, we are losing some force of the muscle. So that is why the tendons are less stretchable than ligaments. Where the ligament and tendon attach to the bone, which we call it the insertion site, you see from muscle, tendon, then they turn into fibrocartilage and calcified cartilage, and then bone. This gradual transition is for gradual transfer of bone, of load. And this gradual transfer of load and stress prevents sudden rupture when the property of the materials are changing from calcified cartilage to bone, from fibrocartilage to calcified cartilage. So um, uh, if we consider muscle, tendon, bone structure, and they are under constant load, constant tension, the weakest part is this junction of junction of the tendon to muscle and to bone. And among these two, junction between tendon and muscle is the weakest part of our skeleton. And then junction between tendon and bone is the second weakest part. So if a rupture wants to happen, it first happens in musculotendon junction, then in the tendon bone junction, and the last part is inside the tendon. That is why when we have a rupture of tendon, not ligament, ligament is different. When we have rupture of tendon in the body, we look for a predisposing factor, like a disease, like a medication, to weaken this tendon. Because if it was normal before it ruptures, these two areas must have been ruptured. So when we have rupture in tendon without rupture in these two junctions, it means the tendon has a disease inside it. By disease, I mean a weakness, whatever the cause was. As you see here, this is an electron microscope view of collagen fibers in tendon and ligament, and you see this wavy pattern, slightly wavy pattern, and it is very important for us. Beside this slightly wavy pattern, you remember the structure of the collagen, and they were like palisading over each other. So these two arrangements are important for the behavior of the collagen under tension. Sorry, behavior of the tendon and ligament under tension, not collagen. When we apply tension load on tendon or ligament, I say tendon, but it is correct about the ligament. The stress strain behavior curve has such a shape. In the first region that we call toe region, the tendon stretches easily. And with a small stress, you have a large strain. This is because of these wavy arrangements of the ligaments, and they, under a stretch, they straighten. They become straight. And it easily happens. So this area is because of the arrangements of collagen fibers. And since this wavy arrangement is not uniform in different parts of the ligaments and different collagen fibers, the modulus of elasticity here is not constant. It increases gradually because as the ligaments or tendon stretches, more wavy parts are straightened and the tendon becomes stiffer and stiffer. If the strain increases between 2 and 4%, now we have a linear part. The first part was because of the wavy arrangement of the collagen fibers. The second part is because of this arrangement, the palisading arrangement, and now we are stretching the collagen fibrils, the small fibers forming the collagen fibers, and we are stretching them and sliding them over each other. Actually, we are increasing the length of the collagen fibers, but we are not breaking them. We are just sliding them over each other. So since this is a sliding pattern, here the modulus of elasticity is linear and increases constantly until it reaches to the end of this sliding movement. When the first fiber starts to fail, starts to break, the third part starts. And here is the yield point for the tendon or ligament. In this point, there is no return to the original shape. When you remove the load, the tendon has failed in some fibers. They cannot return to its original shape. So actually, they are showing plastic deformity. And if we continue the load, more and more fibers fail, and at the end, the tendon will fail and will rupture. So When we stretch the tendon, for example, I am contracting my forearm muscle and I am flexing my fingers, the tendons connecting my forearm muscles to my fingers are under a stretch. If the load is, uh, let's consider that I am holding something with my finger. So I am flexing it and I am holding something with my finger. If it is light, my ligament will be stretched based on the contraction of the muscle in toe region. If it is heavier, my tendon may enter the linear region. But if it is too heavy, my tendon may enter the plastic region and starts to be injured, starts to be failed. And gradually it continues and continues until my tendon fails. And this is another representation. And as you see, uh, this far phase toe region is for uh, straightening of the fiber. The second part, the linear part, is for sliding the fibrils over each other. The third part, the plastic deformation, is microscopic failure, micro tears, and the last part is macroscopic failure, which is the rupture. Again, about the hysteresis. Since tendon is viscoelastic material, it undergoes hysteresis. And I said under each loading cycle, 7% of the load in tendon is dissipated as heat. So for one cycle, it's not important. For second cycle, no. But if the tendon or ligament is under repetitive load, for example, during marathon running, or a person is performing an exercise that needs uh, repetitive motions in the tendon, repetitive contraction in the muscle and tension in the tendon. In the first load, it returns here, the second one here, and it continues. This continuing means with physiologic loading, the person is not applying the abnormal loading. The load is physiologic. It is normal running, but it is marathon running, 42 kilometers. So with repetitive motions, gradually the tendon doesn't return to its not only normal condition, to abnormal strain, because it is load to stress to a strain. So gradually the strain remains in the tendon and it accumulates until the tendon or ligament fails. This is another mechanism for tendon and ligament failure, and it is very common in repetitive loading of ligaments. People who, especially if they are not prepared for that exercise, they may have problem with this, and they think they are applying physiologic load, but the accumulation of hysteresis causes injury and fails the ligament. And again, like bone and cartilage, when the tendon and ligament are under tension, the cells detect this tension and remodel themselves and regenerate. And if they are not under load, they gradually degenerate. This is, again, important for us. When we have an injury in the tendon, you remember for bone, we said in bone healing, when the bone, we have a fracture, and the bone heals, gradually it returns to its normal arrangement of osteons. For ligaments, the same thing happens. Gradually, the orientation of collagen fibers, which were along the length of the tendon and ligament, return to its normal orientation, because during the repair, during the injury, they were ruptured. During the repair, new tissue was formed that has spontaneous and disorganized arrangement of the fibers. But under constant loading and repetitive loading, this arrangement of collagen fibers return to the original arrangement along the length of the ligament. About the muscles are not a tissue for uh, tolerating the load like cartilage, bone, and ligament. They are for generating load. So uh, we don't discuss their biomechanical properties based on their mechanical property. We discuss it based on their uh, ability to generate load. So uh, you remember the microscopic structure of uh, two types of fibers, thin and thick filaments, myosin and actin filaments, and they slide over each other in a complex uh, process, and they cause shortening of the whole muscle cell, and it is called muscle contraction, and it generates force for our movement. Um, One important thing about the muscle is the length of the muscle determines the load that it produces. The length of the muscle actually determines the amount of overlap between thin and thick filaments. If they have increased overlap, they are actually inefficient, and they create a linear increase while we are stretching them. If this is the amount of stretch or increasing length of the muscle, and this is the amount of force the muscle produces for us. By stretching, we are changing the amount of overlap between these two filaments. And if we decrease this overlap, it means the amount of attachment between these two is decreased. When the attachment decreases, the force generated will be decreased. So when the muscle creates most force is when the overlap is optimal. The optimal overlap is when all the myosin is covered by actin. It's here. If we have more overlap here, it decreases the tension, because first, uh, we have, although we have optimal overlap, but the muscle length is decreased. And it is not, you will see later why it is not good for us. The optimal force will be when there is the optimal overlap. No, no excessive overlap. The first point or beginning of this, or other word, end of this thin filament is at the beginning of thick filament. This is the optimal location, which is here. If we increase the length of the muscle or stretch it, it means that this overlap will be decreased. And this decrease will show it as decrease in the force that the muscle is generating. And remember, this tension, it means active tension, or the force that the muscle is generating. But when we are stretching the muscle is a tissue and it has a passive force. So the active force generated by the muscle while we are stretching it decreases after a certain point. But since the passive stretch is built up, the total stretch will increase gradually. So the red one is active force that the muscle is producing, which first increases with the stretching up until the optimal overlap between the thin and thick filaments happens. And then for a while, it remains constant. And then after the overlap begins to decrease, the force generated decreases. This is the active force. Passive force gradually builds up in the muscle as a passive elastic tissue. And the sum of these two creates this curve for the whole or combined active and passive force in the muscle for us. Here I have included some complementary video for you. You can watch them later. These are some artificial muscles, and you can compare. I show them in all my classes because I want the students to know how far we are from creating a real muscle. You are now familiar with the mechanism of muscle contraction and how the cells work. And you see the muscles, artificial muscles that are produced are far, far from our true muscles. You may say, yes, we are far from, but what about other tissues? In the other tissues, we are very closer. For example, for bone, whatever we have produced is very closer to bone. For ligament, we are not as close as bone, but we are close. But for muscle, we are nowhere. When you watch the videos, you see, if you are interested, if you watch the videos, you see how far we are. Okay, if you have any question, please ask. Otherwise, I explain something for you. No?
Yeah,
Yes.
I'm sorry. Just for the Monday, for the presentation of the research on Monday,
Yes.
like how much of our information do you actually want us to show? Because what I was doing currently, I was condensing a good chunk of what I found, but I wasn't sure if like you want everything or you just want like the main stuff we find, or
I
in
want you
terms
to
of
show
presenting our
me
research.
maybe if I am talking in the scale of a slide in 4 to 5 slides, okay? 5 short
Okay.
slides to explain the current position of literature about your topic. Maybe the literature has solved your topic and you don't know, or there is nothing in it, or there are some researchers, but you don't need to bring all of them. Just uh, an abstract in 4 or 5 slides to explain the current position of literature, current idea in literature about your topic. Just that.
Okay.
May you open your microphone? All of you. Okay, thank you. You all received the email from Precision OS Company, yes?
Yes.
Yes.
And you received the list of 21 apps in email, yes? You
Yes.
need there was a
Yes.
link. You had to click on the link to accept it in your account. You did it,
I
yes?
Mm-hmm.
I
And it
think they only
worked.
sent 19.
19, maybe
Was it
19.
21 or
Uh,
okay?
I don't
Because
know. If it was for me was 22. Maybe one of them or two of them were for admin. How many did you receive, Jacob?
I can double check in the email.
yeah, because me personally, I got 19. So
19. You have 19. So I want to be sure that you have installed all the apps. Um, and have you opened them on your MetaQuest or not? And it
mhm.
works? Okay. So you are ready for tomorrow to start the VR experience, yes? You are all ready?
Yeah.
Uh, just let's see how many apps, Jacob. How many apps, Gabby, you received? And
I
Nick,
think I'm
20?
almost there. I have 22.
22.
Yeah, I'm gonna see if any of them aren't with the link though. First one.
I also have
Because I
22.
have 22
Yeah.
on my app, on my phone, on the app, I have 22. Let me see. 1, 2, 3, 4, 5, 6. I have 23. So may you contact Olu. He is the support person in Precision OS, and ask him about, may you can provide the list of the apps you received and check with him if there are any apps you haven't received, and be sure that you receive all of them, okay?
Okay, so you said email who?
The support system, the support email you received from the Precision OS yesterday. The person who
Okay.
sent it, the name is Olu, O-L-U. He's a very nice guy and he spends times to solve the problems. So,
Okay.
and also you have created the account in precision.link, yes?
Yes.
The precision.link account is for connecting your apps with my app. I will be the admin or the professor, you will be the student, and when you perform the surgeries, I can see how you perform and I can follow you up, okay? That account is for this connection between our apps. Okay, that's it. I
All
just
right.
want to make sure that you received all the apps. If you have received less than 23, please contact Olo to be sure that everything is okay. Okay?
Yeah.
I don't want you to miss anything on this app because you have paid for it. No question? Okay. See you tomorrow at 6:30. We will have a short discussion about the intramedullary nailing to introduce intramedullary nailing concept to you. And then we move on to VR to see what we can do. Okay. And also for Meta, you have installed the Meta app on your phone, yes?
Yes.
Mhm.
And you know, on your
Yes.
phone, you can capture whatever you want as a video. Whatever you are performing on Meta Quest, you can capture on your phone as a video and you can watch it later. Okay? Have a great evening. See you tomorrow.
You too.
Have a good night. See you
Thank you,
tomorrow.
Preston.
Bye.
Have
Thank
a good
you.
night.
Bye.